All right, so what we're going to cover in this example is a repeated measures ANOVA for one IV only. So I'm going to walk through how to do this in R and explain a little bit as I go. So a quick note on repeated measures designs is that sometimes people find it difficult to separate the IV and the DV because the IV is each group's measurement and the DV is the actual score within each group. And so what we're going to do is take data that's in wide format, where each person is their own row and each column is a different measurement, and move it into long format, which sort of forces you to think about IV and DV. Partially too because you have to have it that way to make it run. So a nice thing about repeated measures designs is that they're more powerful, so we need less people because we're measuring those same people a couple of times. So we're going to reduce that error variance, that within subjects variance, because we're controlling for the fact that people are themselves. And so we're taking out the peopleness variance. The drawback here is that there's an interaction with the study design sometimes, where if I'm taking that same test over and over again, of course I'm going to get better. Or maybe I'll get worse because I'm bored. So I kind of have to balance out carryover effects where I put each level after every other level, and fatigue. So there's kind of a trade-off here. We get more power for using repeated measures designs, but sometimes the design itself can affect the way people perform. So let's scroll down a little bit. In this particular example, participants were tested on their pulse, and we just made them do different things. So this is a very simple study to kind of show you how this works. So sometimes we showed them a neutral picture like a toaster, and other times we showed them cute puppy pictures, and then other times we showed them pictures of war. So we would expect different pulse rates for these different pictures. So were there differences in pulse rate for each participant across those stimuli is our question. So we're going to work with our repeated measures 1 data. Our IV type is going to be neutral, negative, and positive stimuli. And our dependent variable is going to be that heart rate. But before we do that, let's start by looking at power. So we're going to use G-power to do this. The way we're going to make this work is we're going to click through, and I can't make G-power any bigger, so I'm just going to do my best here and pick F-test. A statistical test is repeated measures within factors. We want to estimate their effect size because the effect size here is listed in Cohen's F, which is not what we're used to working with. So we want to hit determine and then click direct, and now we can enter eta squared. So this particular example, we're going to start with a large effect size. So we're going to use 0.25. Calculate and transfer to main window, and that changes the F size over here. Now alpha we're going to leave as 0.05. Power we're going to leave as 1 minus beta at 0.2, so power is 80%. So we're going to leave this one alone. We're going to change this one to 0.80. Number of groups, let me go back over here, is the number of IVs. So in this case, it's 1. And then the number of measurements is the number of levels. So we have 1, 2, 3. Our correlation among repeated measures is the correlation between levels. So generally you wouldn't know that, but maybe if you had done previous research you would. So you can look at a pilot study, or you can just guess. So 0.5 to 0.7 is a good estimate if you're giving that same test multiple times. So we're going to leave this at 0.5 for our particular example. The non-sporicity correction is epsilon. You'll never really know that number. So we're just going to leave it at 1. All right, so I'm going to hit calculate. If you're on a Mac, yes, it's way down here hidden. You can just hit enter in any one of these windows and it will also calculate. So it tells me that I need 7 people to make this work. Now, I probably should have more than 7, right? Because of normality assumptions. And 7 people is kind of a stretch for small samples. But that's what it's saying we need to find a large effect. Okay. So test yourself really quick and see what happens if I change the effect size to small and a high correlation among measures. So small over here will be 0.01. I calculate and transfer to main. And then a high correlation between measures at 0.8. Now I need 66 people. So make sure that you can get the same numbers that I'm getting here. So we need 7 people for a large effect size, and hopefully that's what we actually have. Okay. So I'm going to walk through running this test. Now in this Word document, I have kind of like step-by-step what we're doing, but we'll kind of flip back and forth between this and RStudio. Okay. So we're going to use that summary to get some basic information for the data and check out our min and max, because we want to make sure that no one's pulse is 0 or negatives. And some of them do appear high because this data is totally made up. Okay. So let me get this loaded. I'm going to load, do my working directory, and it tells me my working directory is wrong because I'm sure I've moved this file. So let me reset that bad boy. But you'll want to set your own working directory here. Let me just clear this stuff out. Just updating these notes. There we go. All right, let's import our data and look at a summary. Whoa, what is happening? I must have hit a magic button. Okay, it's going to run the entire script. Great. Okay. Let's try again. There we go. Now let's look at just a summary because that's all I really want to do. Okay. So my summary over here shows me that nobody looks dead, although some of these people's heart rates are real high because it's fake data. But we just want to make sure there weren't any negatives. Okay. With that summary function, I can see that there's no missing data, so I don't really need to do anything about missing data. However, if I had missing data, I would basically just have to exclude them because 3 columns is not enough to make up data points with mice. Now, the data set's in wide format, which means that each person gets their own row. And that's how you want to screen it for outliers if you can, because that gives me several columns to work with. And now I can use Mahalanobis distance to examine each participant by controlling for correlated error. So it continues to account for the fact that I am person 1 all 3 times. So remember, to create those scores, we're going to save them as Mahal. So to run this as Mahalanobis, the name of the data set. Remember, you're changing things in italics here. Call means and cove of the data set. And we don't have any columns to exclude because we don't have any categorical columns. So that's what code I have typed up in here. And now I've created a list of Mahalanobis values, but I have to come up with some sort of cutoff score for those values. So we're going to use q chi-square to come up with our cutoff score. We're doing 1 minus the big important rule. And our degrees of freedom is the number of variables that we put into that. So here it's going to be 3, 1 for each level. And so our cutoff score is 1627 with 3 degrees of freedom. So when I ask you on your homework what those numbers are, that's how you would get them. We're going to run a summary here of the number of people less than our cutoff. And it says that everyone is less than the cutoff score, so we have no outliers. If we had someone in the false column, that would indicate that their score is higher than our cutoff score and they're an outlier. So this just tells me how many I'm excluding. I'm going to keep using that code from data screening though and pretend to exclude people. But when I run this no out line, it's going to keep the same number of participants. So if you look down here in your environment window, or if you're using traditional R Studio, it's going to be up here at the top. There's still 18 people in each data set. Okay, go back over here. Okay, we did all this. So we do have to look at correlations because we're using a repeated measures design. But before we talked in the lecture, we talked about mainly we just don't want them to be perfectly correlated because otherwise it kind of messes things up. So here we're just making sure that nothing is a 1. We're going to use our core function to create those correlations, so core of our data set. We don't have to exclude any columns because there are no categorical columns. And then we'll use our symbols for numbers function to look at the symbols chart, and we want to look for anything that is not, basically we don't want any ones. So I've got pluses and stars here. So the star is 0.9 to 0.95, and the plus is 0.8 to 0.9. And this is a relatively small table, so I could open the entire thing and look at it. So we do have some very high numbers here because this is made up data, but none of those are above 1. Or, well, gosh, I hope not mathematically, but none of them are 1. So essentially these ones on the diagonal should be there, and we want to make sure these ones on the off diagonal are not 1. So everything looks okay. Now going back to power, you could use the lowest number here for our power calculation. So we could use 0.85 because it's the lowest number we've gotten in this data set, instead of 0.5 like we did at the beginning. Okay, let's set up the rest of our assumptions. So we're going to create a random variable to test our assumptions against and run that fake regression like we did last time in data screening, and calculate our standard residuals and create our fitted values. So this is our traditional setup so that we can look at normality and linearity. So nothing too exciting about that. It matches what we did for between subjects as well as our data screening video. In our normality though, we're going to take a histogram of those standardized residuals. Remember, when we standardize those residuals, we want them to be centered over 0 and usually between 2 and 2. So let's look at what that histogram looks like. Now, everybody's going to get a slightly different picture because we're using random numbers. If you aren't sure about your picture, try running this a couple of times and see kind of what the general gist is. Whatever you answer on your homework should match the picture that you show me though. Okay, so let's look at this one. In this particular example, I would have said this is a bit positively skewed because there's no data over here. And the one that I've got on the screen here is actually a bit negatively skewed. So the skew is probably dependent on the random run, but every time I've run it, I've gotten a little bit of skew. And this one's like almost totally uniform, which is unusual as well. And so I can tell that maybe I have some problems with normality. There's a little bit of skew there. And I don't have 30 people. I only have 18, so that's problematic as well. Okay, so I would say this is a little skewed. Okay. To get linearity, what we're going to do is use the QQ norm function on our standardized residuals. And we're going to add the AB line so that we can have something to compare against. And that looks pretty good because the dots are mostly on the line between 2 and 2. Okay, these two bad boys on the ends are the only ones off the line. And if I come down to my plot that I made from a different random run, again, just one bad boy out here, but mostly they're on the line. Now to get homogeneity and homoscedasticity, we're going to make that residual graph. For homogeneity, we're going to look around 0. So I got this 1, 3 up here. He's kind of annoying, but most of the data is between 1 and 1. Okay. So don't let one data point ruin your whole picture. So don't let one bad thing ruin your whole day. I would say this data is mostly homogeneic because it's between 1 and 1 and 2 and 2, except for one data point. Now again, you can always run this again. Now you shouldn't run this until you get what you like. You should run it a couple times if you just aren't sure. If I run it again, most of the data is between 2 and 2 and 2 and 2. So that one data point isn't problematic. Now, homoscedasticity-wise, this is a hot mess, right? So it kind of looks like a flying V at the moment. But in ANOVA, we're generally more concerned with homogeneity. Okay? And most of the time people don't talk about homoscedasticity because when you're working with categorical variables, they're kind of the same thing. In general, when you have a small number of people, it's hard to tell. So with only 18 data points, it's kind of hard to tell. Okay. Now, one thing we're going to add here is Mockley's test. Mockley's test is a measure of what's called sporicity. Sporicity is sort of homogeneity for repeated measures. And where sporicity works is called compound symmetry. So compound symmetry is 2 parts to homogeneity for repeated measures. It says that the correlation between all levels are equal. So 1 to 2, 1 to 3, 1 to 4, those correlations are all equal to each other. The second part, which is a little trickier, is not that the variances between groups are all equal, it's that the variances of the difference scores are equal. So if I take time 1 minus time 2 and calculate that variance, and then time 1 minus time 3 and calculate that variance, etc., those difference scores variances are equal. So it's called compound symmetry because there's symmetry in the correlations and the variance of the difference scores, and compound because there's more than one. So there's 2 different things that you have to meet. However, it's very difficult to meet this assumption because let's say the best example of this I can come up with is a smoking cessation program or a weight loss program or anything where you're trying to push people's scores all the way to the top or all the way to the bottom. Okay. So let's say you've got a tutoring program. So you're trying to make everybody get an A. Well, what happens when you have these ceiling and floor effects is that the variance naturally decreases across time. So if you think about a weight loss program, people are going to be all over the place. But then as everyone starts to lose weight, the scores are going to get closer and closer to a smaller number. Not 0, clearly, but a smaller number. If you're trying to get people to quit smoking, you are trying to approach 0. And so often the variances get smaller or larger across levels. And that will often break sporicity. So sometimes people ignore it. So if you're reading a research report, they don't talk about it because they either don't know better or they're ignoring it, which we shouldn't do. But we're gonna talk and look at it ourselves. Okay, so we're gonna get that test automatically with the ANOVA we're about to run, and we're gonna make sure that it looks okay. Now, practical matters getting into the ANOVA. Just like with between subjects, we have to add a participant number to the data if that doesn't have one, because the EZ package does require it. So we're going to add one to our data set the same way we did before by doing the name of the data set. We're going to call it part no, and we're just going to count up from 1 to the end of the data set. And so all that's doing is adding a participant number out here in this last column. Second thing we have to deal with is the fact that the data is in wide format. So this is specific to repeated measures problem, just like with graphs. Anytime you have between subjects data, this is easy because the data is already set up correctly. When you're dealing with repeated measures data, generally each person gets their own row. So we've got to melt that down so that each time point gets its own row. Okay. So each level and participant get their own row, and that's going to actually make it a little more comprehensible in the sense that we will have an IV column and a DV column. Okay. We're going to use that reshape library, and we're going to melt that data set. So what we're going to do here is we're going to melt the data set name. We're going to keep any categorical variable the same. So that's our IV, our participant number under ID here. So all the rest of the columns go under measured. Okay, so measured are the ones that are getting melted into one column. ID are the ones that are getting repeated, and so you got to keep that number with each person. So maybe like gender might be one of those too. Other thing I'm going to do is rename this variable and value because these names suck. So we're going to give these better labels because this is the IV and this is the DV. So now what we want to do is just call those what they are. So it's the picture type and it's their heart rate. So I've just changed the names of the columns. So I'll click down here again, and now I have much better labels for those columns. Now into the business of running the ANOVA. So we're going to use the ezANOVA function in the EZ library. We're going to do data equals the name of the data set here. Our within subject's ID is part number, so we want to include that participant number. Don't confuse WID for within subject's ID. This is just participant number with the within function. So the within argument here is the variables that are repeated. I wish they called this repeated, but within is an appropriate term too. So we're going to put in our IV column name. DV here is always the DV. And remember, leave type equals 3 so that you get the right type of math behind that ANOVA. Okay. So I filled in pick type and heart rate here. Okay. So I'm going to pull this over here, make it a little wider so you can see better what's happening. So the first thing we're going to get is Mockley's test, and I want to look at Mockley's and make sure it's not significant. It is very close, so ignore this little star right here. It is close, but not significant. Remember, the rule is 000, and it's bad. So this one is 001, so it's not less than 001, so it's okay. If I wanted to correct, let's understand what's happening down here since this is new, right? So you're going to get two different corrections. Let me go back to the notes here so you can look at them. Okay. We just talked about this thing, but what are these corrections? Well, GGE is for greenhouse geyser. It's the epsilon value for that. Epsilon is a measure of how non-sporific it is, or it's a measure of sporicity, right? But that's not what we're really going to look at. Instead, we're going to look at the p-value for that. So if I used a greenhouse geyser correction, we would want to see here if p is less than 0.05. The other option is Hunfeld. And the way Hunfeld works, or greenhouse geyser versus Hunfeld, is they're just two different types of corrections. Very similar to corrections for Posthoc tests. These are corrections for sporicity. So you get here under E for both of them a measure of sporicity-ishness. And if they're both less than 0.75, use greenhouse geyser. If they're greater than 0.75, you use Hunfeld. And so if one is under and one is over, take your favorite, pick your favorite one. Hunfeld is a little less restrictive. People like it better. But those are the rules I've seen. So I would look here under epsilon to pick which one to use. So they're both less than 0.75, so I pick greenhouse geyser. And then I would look at the p-value here instead of up here to determine if it's significant. Now you only do that if you need to correct. We don't need to correct, so we're going to ignore it entirely. But if we wanted to use it, what we would do is look at this p-value, which is currently in scientific notation, which we can turn off, instead of the one up here. And then they star them for you, just in case you aren't sure. If I look at it here, totally spelled out. This is clearly less than 0.05. Okay. And so is our original p-value. Okay. We can also look at the way to write up this F test. So under effect it says pick type because that's what I named my IV. DFN is our degrees of freedom numerator, or degrees of freedom model. DFD is the denominator or the error term. F is F. P is our p-value. P less than 0.05 tells me if it's significant, which is good. GES here is generalized least square, or generalized eta squared. Good grief. Generalized least square is a type of math. Generalized eta square or eta squared here. It's significant. So the way we would write that up is F is 2 and 34. And so I'm pulling that from here. So 2 and 34, they're in order, equals F, P less than 0.001, okay. Eta squared equals 0.59. Okay. I said here using a greenhouse geyser correction just to show you how you might write that up. But here we did not need to correct. So also you can do this in AMA format, sorry. So F and then use the little superscripts. Oh, that one's subscript, sorry. Now that we've figured out that our test, our overall test, our omnibus test is significant, we gotta do something else. So now we're going to have to run Posthoc tests to kind of figure out what's happening. And I'm going to make these tables here to help me just kind of keep track of what the heck I'm doing. So we're going to calculate each pairwise combination and compare every mean to every other mean. So here I'm going to calculate and use tapply to get each mean set of means. What we're doing is doing this on the long data set. So here we're going to take length here, but remember that length measures how many people are in each group, but this is a repeated measures design, and so how many people are in each group is actually the same people each time. So just remember that it isn't 8 people in each group, it's 8 people total. Okay, so I'm going to use my tapply function to calculate the means for each level here. So my neutral pictures are 88 heartbeat rate, my positive pictures are 134, my negative pictures are 150 if I round. I have my standard deviations, and there are 18 people total. So there are 18 measurements in each group, but only 18 people total. And so what I've done is just thrown that into a box. So I'm going to compare neutral to positive, neutral to negative, and positive to negative. Okay. Now I have to figure out the post-hoc test and that post-hoc correction. So just looking at these numbers, it seems to be different, but which ones are significantly different? Okay. And then even better, which ones have the biggest effect sizes? Just like with between subjects, we're going to use pairwise t.test. And that will run every pairwise comparison and give us p-values for those. We're using paired equals true because this is a dependent t-test, which is what we want for repeated measures ANOVA. And this is in bold because it shows up on quizzes, right? So you want to make sure that you match the type of ANOVA with the type of post-hoc test. P.adjust method is the correction type. So we're going to use Bonferroni. So I've got dv on my long data, right? So dv, comma, iv, right? Paired equals true, P.adjust method equals Bonferroni. Okay. And this version gives it to me with all 6,000 decimal points. So make sure this says paired t-test. We need to make sure we match the right type of ANOVA. And remember that Bonferroni is adjusting those p-values based on the number of tests that we're running, because we can keep using p less than 0.05. Remember, good grief, these notes with the typos. You can turn off scientific notation, which I've already done. And I'm going to fill in those p-values here in this column. So they're all less than 0.001. And so what does that mean? Well, it means it's significant. And I'm going to look at my means to determine what I would use it to explain to my mom. Right? So if I said this is a significant effect, she would look at me and roll her eyes. So I would say, okay, fine. The positive heart pictures create a higher heart rate than the neutral pictures. And the second one, the negative pictures create a higher heart rate than the neutral pictures. Not too surprising. But in the last one, our negative pictures are creating a much higher heart rate than our positive pictures. So maybe that's surprising, is that these two aren't equal. The negative pictures create a stronger reaction than the positive pictures. Okay. What we're going to do is use that moat library to calculate our effect sizes here. Fix this little typo. And so we've got to run that 3 different times because we have 3 different tests. So we're going to fill in mean 1, mean 2, standard deviation 1, standard deviation 2, n. There's only one n value here because we only have one set of people. Alpha, and then I'm going to delete this because that is the new update to moat. Okay. So we have our means and standard deviations. We can type these in manually. If you've taken one of my classes before and you know how to pull these numbers automatically from tapply, that's fine. Or you can just type them in directly. All right, so I've got those here, so be sure you load the moat library. And so I've just typed in these numbers manually, but like I said, if you know how to save them and pull them, you can do that too. And so when you look at this output, the number you're going to look for up here is D. So it's the very first thing that pops up. But you want to make sure that your numbers look like the ones you're expecting, right? So I typed in 87, I got 87. So it maps onto the numbers from your table you've made over here. So 87 and 16 maps onto 87 and 16. Okay. We're going to pull that D value here. So it's 2.42. And then we're going to run the second one. Come up here, it's 2.79. And then the third one is 0.62. Okay, so 2.42, 2.79, and 0.62. You'll notice that I dropped the negatives because I have the explanation here. The negative is occurring because I did neutral minus positive. And so the effect size here is still large either way. And I think it's better to just tell people the positive heart rate is higher than the neutral heart rate, then try to understand what a negative effect size implies. Now, looking at these numbers, my interpretation is that the positive and negative stimuli are much stronger at like eliciting a heartbeat response in comparison to neutral. But when I compare positive and negative, yes, that's a medium effect size. So the effect sizes here are unreasonably large because it's made up data. But here, this is still a nice medium effect. But the effects here are larger than the effect here. Okay. All right. But the best type of chart we can do here is make a bar chart. And so we're going to use our long data and ggplot. And so at this point, you've had ggplot. And so we're going to just kind of walk through this. So I'm going to load the library. I'm going to use my theme coding to, or my cleanup code. So I've been trying to update all these notes. I like calling it cleanup better because that tells you what the heck it's doing, and it doesn't use the name of the variable here. So we're just going to change that real quick. It doesn't matter, but it helps if you don't overwrite the name of a function. I've learned that one the hard way. So we're going to use the ggplot function, use the name of a data set, IV, comma, DV. So remember with paired t-test, it's DV, comma, IV with, so let me scroll back up to show you where paired t-test is. So DV, comma, IV, derp. This one is X, comma, Y. Okay, so keep those in the right order, but if you do it in the wrong order, believe me, you'll know. To that bar graph, I cut and pasted this essentially from the graphs notes, but I'm going to create the bars by using stat summary. Function of y is the mean. And then I'm going to create my error or confidence bands on those bars, so the error bars, by using function of the data. I'm going to clean that bad boy up using my theme coding, add X and Y labels. And then I'm going to create some some labeling that looks better. So let me run this first without cleaning up the x-axis. And you'll see that these are lowercase. So we want to make our pictures look as professional as possible. So we're going to use scale x discrete here because these are discrete values, and use the labels function in the same order to just capitalize them. You could also use the factor function and refactor them with capitals. That would work as well. So now I've got a nice cute picture with my neutral stimuli are the lowest, positive and the negative are the highest. And so I can compare them fairly easily, and I can see that these two are definitely much larger than this one, and this one, they're about the same across here. One thing I cannot do with repeated measures designs is just look at the error bars here. And in between subjects design, I can see if the confidence intervals overlap, but in repeated measures design, that is not valid. So I had to run some sort of test here to tell if these are different. More importantly, the effect size shows me this is a medium effect between these two and a large effect between positive, negative, and neutral. Okay. All right, and then the Word document walks through this kind of one at a time and explains what's happening in the background with all of these things. So we're going to change this to clean up. so that you can walk through that one piece at a time if you haven't, still not comfortable with plots. But the last thing it has here is an example of a results section. So how you might write this sort of thing up. And walks through using DAV here, because this is D based on the averages as the denominator, and how that might look, including a picture. So when you're working on this for your homework, here's an example of what this should look like. Okay, so that wraps up repeated measures ANOVAs for one-way designs.